Now I have mentioned before that the state variables are not unique, right? Now we will see this mathematically. We have taken an example and we have shown that it is not unique. State variables, we can choose different variables as state variables. But now we will do this mathematically. Okay. So if you rewrite the state equation and the output equations, they are called together, they are called as the dynamic equation, right? So what will be the state equation? X dot is equal to ax plus bu. Here x is the state vector and u is the input vector. And what about the output equation? Output y is equal to cx plus du. Now x is the original state vector for the particular system that we are considering. Okay, consider a system with the following dynamic equations. Okay, so here you can write x is the original state vector. Now we will take a new state vector, but it will be related to the original state vector. Okay, so let us take v is the new state vector and it is related to x as x is equal to m times v. Okay, now you can write x dot is equal to m times v dot. These two, if you substitute in the state equation, then what will the equation, we've taken that as equation 1, then this will become x dot is m v dot is equal to a into x, you can write as m v plus b u. Okay, then what you're going to get? V dot is equal to m inverse a m into v plus m inverse b into u. So you can see that this is in the form of a state equation only, but the new state vector is now v dot. Here you have v, so you can consider this entire m inverse a m as a matrix A bar. Okay, and this m inverse b you can take as b bar. So then how can you write? V dot is equal to a dash into v plus b dash into u. So it is in the same form as the state equation, only that the matrices are now different, system matrices A bar and B bar, right? So this you can call as the new state equation. Then what about the output equation? Equation 2, y is equal to c times x. In place of x you will write as m v plus d u. Okay, so what are you going to get here? Y is equal to cm into v plus du. So you can take cm as c dash, so that you can write this as y is equal to c dash into v plus d dash into u. But here d dash is simply d only. Okay, there is no change in d. So here we have the new output equation. Okay, so these are the new state and output equations in terms of the new state vector v. This is how we know that the state variables need not necessarily be unique. Okay, according to the choice of state variables, these matrices A, B, C and D will also change. Now we have seen the matrix M. How was it relating x and v? Like this, x is equal to m into v. Okay, now this matrix M, it can be different values of matrix M will give you different state vectors. Okay, so that is why it is called as the transformation matrix. And the process of obtaining new set of state vectors, it is called as the similarity transformation. So you can write similarity transformation. It is the process of obtaining new set of state variables. Okay. Next, one important point you need to know here is the invariance property of similarity transformation. So when you do the similarity transformation, the characteristic equation and the transfer function, they are not going to change. Okay. So because characteristic equation and transfer function, they define the system, they define the behavior of the system. Whenever you are using a new state variable, it should not, right? It should not affect the behavior, how we have described that particular system. So we will try to see if it is indeed satisfying. So if you take the characteristic equation, what was the old characteristic equation? Det of Si minus A is equal to 0, right? A, B, C, D are the original system matrices. And let us take A dash, B dash, C dash and D dash as the new matrices. How will they be related to the original matrices? They will be related as A dash is equal to some M inverse AM. M is a similarity transformation matrix. B bar is M inverse B. C bar is C into M. And finally D bar is simply equal to D. Here M is transformation matrix. Okay. So now this was the original characteristic equation. Now what will be the new characteristic equation? The new characteristic equation is going to be Si minus A bar. Okay. Now what is, this is equal to 0. Now what is Si minus what is A dash? It is M inverse A into M. This is equal to 0. Okay. So now I you can write as M inverse into M. S into M inverse into M. Inverse of a matrix into that matrix will give you identity matrix. So this is minus M inverse AM is equal to 0. Now if you take out the M inverse common, then what will you get? M inverse SM minus AM. Here you can see that M is common, you can take it out. But be aware of the order, right? How did we take it common? M inverse we have written before this term, right? And M we have taken after right side of this term, because the order of multiplication for a matrix is important. Okay. So this is going to be equal to 0. Now there are three different matrices. You take the determinant. It will be equal to, if you take the determinant of A, B, C, A into B into C, you can write it as determinant of A into determinant of B into determinant of C. Okay. So what are you going to get here? Determinant of M inverse into determinant of Si minus A inverse into determinant of M is equal to 0. Now all the three are scalars. M inverse and M, the determinants of each of them will give you 1. So this you are going to get Si minus A is equal to 0, since determinants of the inverse and its own matrix is equal to simply 1. So we got the same equation, the original equation only you got. Okay. So that is how the characteristic equation is not going to change. Now what about the transfer function? What was the transfer function? We found it as C into Si minus A inverse B plus D. Now this is the original transfer function. Now what will be the new transfer function? You are going to use A dash, B dash, C dash and D dash. Okay. So what is it going to be? C dash Si minus A dash inverse B dash plus D dash. So do not confuse with the transpose. Okay. A dash, B dash, C dash we are taking as different matrices, not the transposes of A, B and C and D. Okay. Now in place of the new matrices, you will write in terms of M into the original matrices. Okay. So what is C dash? C dash is C times M. Si minus what is A? A dash, it is M inverse AM inverse. B dash is M inverse B plus D dash is D. Now here you can see this entire matrix inverse into another matrix inverse. So whenever you have two matrices, let us say X into Y inverse you have to write, then how will you write? Y inverse X inverse. So now we have this form, Y inverse X inverse. Okay. So how you can write? These both you can write into a single inverse form. Okay. So what will it become? Cm into M Si minus M inverse Am. This whole thing will be inverse B plus D. Now M if you send inside, then you're going to get Cm Sm minus M into M inverse is going to be Am inverse B plus D. Okay. Now here you can take M common. So what you're going to get? Si minus A into M inverse B plus D. Now we have xy inverse form. Then how can you write this? This implies Cm into M inverse into Si minus A inverse B plus D. Okay. So now you have the final form. M into M inverse will give you an identity matrix. So here you're going to get C times Si minus A whole inverse B plus D. So this is same as the original transfer function. So the transfer function is also not changing. Okay.